Welcome everybody. Delighted to see all of you again who are back for another amazing day of quantum brain food, as I describe it, right? We have several keynotes by leaders in the space. We have tech tracks, so I'll give you more detail on those. Those are more technically oriented, specific kinds of conversations that are going on in the auditorium down the hall. Some of you may have seen or participated in them yesterday. Several panels as well, so lots of great content. I want to start by introducing our first speaker, Julian van Velzen. He's the director of Quantum Lab at Capgemini, and his talk is titled From Quantum Promise to Practical Impact, Bridging the Value Gap. So please join me in welcoming Julian.
Good morning, everyone. I hope you're just as excited for today as I am after yesterday. So my name is Julian van Velzen. I lead a quantum team at Capgemini. The point that I would try to address today is that we briefly touched on this in the panel yesterday. I think we are now at a stage where these machines are very sophisticated, doing amazing things, but the question is, how are we going to make them useful? And I think there's actually a widening gap between the capabilities of these machines and our capability of using them, and so we must be stepping up to make sure that we will close that gap. And then in particular related to, or at least this talk is particularly related to material design, a bit towards the maritime industry. So maybe first a few words about Capgemini. Capgemini is a big company. Maybe some of you know it. Yesterday was mentioned as a consulting company, but in fact the majority of the things that we do are related to technology development, and then a big part more about engineering services. And so we have a long history in things like material design, combinatory optimization, pharmaceutical R&D, quantitative finance, computational fluid dynamics, these type of topics. Not necessarily quantum, but in the classical sense. And so, of course, that's a reason why we set up a quantum team. And of course, across these technology areas in different industries, in particular also the maritime industry. And so that's why we set up a quantum team. And so the point is to have sort of an internal startup to try to make sense what this technology means for ourselves, but also for our clients. I often use this sort of graphic, this cartoon image to show that the point is trying to sort of tunnel through this barrier and go in a straight line to usefulness. If only I knew how exactly that graph would look like, I would be a different man. And of course, I have no idea. But at least it does help that as a company, we do not depend on selling hardware. We do not depend on one type of modality. We do not depend on selling algorithmic suites or anything like that, which makes us able to be a bit more independent. And I would say being able to see a little bit more, when there's hype and less hype, or at least I'd like to think so. And that's how we try to execute. And so it really is a sort of a startup within a big company. And most of all, what we try to do is from the application first. So that's another key point that I try to address in this talk, is that I think too long the industry has been a hammer looking for a needle, and I think we need to turn it around and trying to find what is the application, and then is there actually any role for quantum in these applications and workflows. So mostly I like to talk about material design because I think that's, material chemistry is one of the most promising area. From this picture from BCG, you see that at technology maturation will be $500 billion created, but then 2/3 of this relates to chemistry and material science across different sectors. Right, so think about materials in aerospace, automotive, corrosion, extremely relevant to maritime industry, of course, computational fluid dynamics as well, all kinds of complex chemistries in catalysis, energy conversions, etc. But the question is, how can quantum computing really contribute to this? Right? I mean, if we turn it around and start at the application, what we want to do is to develop new materials that are innovative, they're stable, they're economically viable, and that requires much more than just some quantum computations. If we look in, some materials are being developed. I don't know, solid-state batteries. I've heard about these for decades, right? And we still don't have them because maybe they degrade over time. We have a project on perovskite photovoltaics, a similar story, right? I mean, it's a beautiful idea, but when you start manufacturing it, it's actually not so simple. So trying to sort of create the industrial reality towards an actual computation, that it's a long distance. And so the first step towards that is trying to get these computational workflows. And that is much more than a couple of transition states or energies. It's really getting informed decisions about which type of material and which type of material properties we might need. And by the way, it's a massive design space, right? So if we have any materials, we typically tens of thousands of candidates where we want to screen and want to process. Many more than we could ever run through a quantum computer, right? So we have massive design spaces, massive computational workflows, and the hope is, of course, that we have a very small part of which we can run to a quantum computer. But even then, it's not going to be easy because, almost all of our sort of experiments where we started with the workflow and try to do resource estimation of the quantum algorithm, we end up with hundreds of billions of gates, and even if it's hundreds of billions of gates, if we consider all the error correction overhead, it's very difficult to make it economically viable. Nonetheless, I mean, I'm here because I'm super optimistic about what this technology can do, but I just want to emphasize that it's not going to be so easy, and we really have to be extremely strategic on how we use quantum computations within these workflows. So I think the first thing that I wanted to touch a bit about is that maybe I'll try to go a bit high over and then go a bit more in depth, and I have a couple of more scientific things later. But I think that the high over trend that we are working on with clients is that in the end, quantum is just one tool, but the disruption that we are seeing in material design is really that there is this converging of technologies across AI, across high-performance compute and simulations, and across automation of labs that is driving this new way of developing materials. And it used to go really iteratively, right? You would design something, then manufacture it, test it for a specific purpose and properties, analyze these results, send it back to the lab, and repeat this process endlessly. But increasingly, I guess that whole process is mixed up and converging. So instead of design, we have much stronger computational design, where we use AI maybe to screen through large data sets, create hypotheses of new structures for materials from tens of thousands of candidates. Maybe use high-performance computations to design new properties of those materials. And potentially, there's some parts of these workflows then can be run on a quantum computer. And they're both good at their own thing, right? So AI, we know that we can maybe simulate large data sets where there's well-documented data, but high-performance compute and maybe more rigorous simulation can be really helpful to complement this, to understand what is happening actually at the scientific and at the chemistry and physical level, to complement these AI models. And then to create some properties predictions. And then we can use this to test these materials, create some hypotheses. And by the way, this doesn't have to be trying to build a material and test if that property is what it is. Maybe it could be a hypothesis to see that something that it isn't, right? Some test that at least helps us inform if our models are right. So it's really the whole process turned upside down. Where then again the AI is trained again on the new data that we generated with high-performance compute, including quantum in the future. And I think this is really where we have to think about how we integrate quantum, because if we don't take this as a larger reality, then it's just going to be one chemistry calculation. So then to think about how where quantum computing will fit in, I think the original motivation of where quantum computing would be useful for is to simulate quantum mechanics, right? And then in particularly strongly correlated systems, so really complex physical and chemistry systems. This was the original motivation 40 years ago, and I think that's still true, that this is our best shot for quantum computation. So anything that relates to complex systems where there's maybe transition ions, or maybe when there's light matter interactions, phototoxicity, photodegradation, all these complex systems where there's these interaction between electrons that are really hard to capture using classical methods. But the problem is these all happen at this atomic scale. And how is this going to make a boat or a ship have less maintenance requirements? Right? There's a long distance between that. And I think a very natural way to connect these type of simulations with the macroscopic scale is through these multiscale modeling. And so the idea here is that in the end, any physical system has these different mechanisms at different length scales that are happening simultaneously. So at the nanoscale, we have these quantum mechanical simulations, and we have a combination of quantum chemistry tooling like DFT, density functional theory, to use. Whereas at the macromolecular and the larger scales, we use finite element method models and multiphysics up until we go to the system level. And so there's all these different types of simulations that are working across at different length scales at the same time, and they are connecting to each other. And we have to think about how this data flows up and down the ladder, right? So it's a bidirectional information stream. On the one hand, we get information that comes from the system scale that informs how this atomic scale behaves, and the other way around as well. Okay, so to make this a bit more real, I thought I'd go into a couple of use cases, things that we worked on to see how this makes sense. And so the first one is on corrosion. I think this was mentioned already a few times as a use case, because it's such an interesting case. There's really complex chemistry going on, and really a massive potential business case, right? It's estimated to be $1.3 trillion globally of cost. So a couple percent of the total GDP. And so for Airbus, this is 50% of the recurring cost of lifespan of maintenance of these planes. And so, in a ship, I guess it's probably just as bad because there's all these interactions with water. But it's a very complex reaction, and something that is naturally multi-scale, right? So there's a very sort of even perhaps a mental connection between, on the one hand, we have this chemistry, these interactions and this oxidation at the molecular scale or the nanoscale, and the other hand, we have these ships that require maintenance. And so the idea here was, can we connect these models? And so Airbus uses these finite element method models to describe these materials, but they depend on the oxygen reduction reaction, which is this, and I think Elvira mentioned this as well, which is this chemistry reaction at the molecular scale, to connect them and ultimately to save maintenance costs. And so the first thing we did was to see, is this really true, right? And so we did a sensitivity analysis of these finite element method models to see to what extent do they depend on the accuracy of this oxygen reduction reaction. And so what you see here on the right is that sensitivity analysis. So you see the degradation over time, and you see in the middle line is the true parameter, so 0.18. And then if you have a 20% off in your parameter, you see that over time, the degradation process completely diverges. And so you get a completely wrong image. So the point of this image is that these type of finite element method models critically depend on these type of macroscopic or nanoscopic parameters, right? So if you get this wrong, your finite element method is useless. And so at this stage, they use experimental testing to get these type of parameters, but that's very not so easy to use, right? It's costly, it's time-consuming, and if you get it wrong, if you get it slightly wrong, only a couple percent off, your method will be worthless over time. And so the idea is, can we replace this parameter estimation using a quantum chemistry pipeline, eventually accelerated using quantum computation? And so I guess even if you have comparable performance in this parameter, you already have a value, right? Because you can do your models and you can play around with different parameters like pH and other type of things. So even if you have comparable performance, it's already very valuable to replace physical measurements. But of course, the hope is that with quantum computing over time, we can improve this. And so we have this quantum chemistry pipeline that we're working on. So going all the way from a computational model, trying to describe the model with different levels of accuracy, optimizing the geometries, using classical chemistry solution, modeling the oxygen reduction reaction and its pathways, choosing different embedding methods, so choosing methods to think about how can we use a quantum chemistry together with quantum computing technologies to both address specific parts of the system, so that we use the high accuracy where it's really needed, and then finally to run it. So on the bottom right, you see some results of this initial paper. So as you can probably not see, maybe it's too small, but it's some pretty big numbers on there. So circuit depths that are certainly out of range for today's or tomorrow's computers. But there's a lot of room for improvement here as well. You know, for a company like Airbus, you know, their life cycles are 30 years, right? So if this takes a couple more years to build, then that's fine. Because the consequences are so massive. So this was one example where we tried to connect these simulations from atomic scale through system scale via finite element method to macro scale. But I have a couple of other examples which is more related to AI. Maybe there's a question. Yes, I mean, this is all resource estimation that we did using, I think using these Azure resource estimating package. And then these different stars are for, I think these are for the different qubits, so different types of, so the blue are for T factories. Oh, is better? Oh yeah. And the other for algorithmic qubits. I would welcome the paper, which is on the top, to different this. Let me first go to this one. So another example where we thought about how can we combine the nanoscopic scale with macroscopic effects was for these metalloenzymes. And metalloenzymes are interesting because they have these metallic core with these transition state atoms, and these are very complex atoms, right? Because they have these open, these very complex electronic structures, and they make them very hard to simulate using classical solutions. But they also make them very reactive and potent. And so we could think about many interesting use cases for across many industries actually, but particularly also in maritime, like biofuel production, corrosion inhibition, maybe cleaning up of pollution, all kinds of catalysis type of effects. And so the work that we did here was first to start with, can we design these enzymes using things like AlphaFold and these AI type of models to predict these structures? Because that's what we know the AI is very good at. But what we think they're not very good at is to calculate things like catalytic potential, because that's really much more interactions and things where there's no data set available that we can predict these things. And so we would use that. We would extract features from those systems that we would then feed into a AI model to predict these catalytic potential. And so this is another sort of workflow where we combine AI, where we use quantum computers at the nanoscopic scale to generate data sets and feature sets that would feed into AI at larger scales to predict properties. And so we go into another example, which is a bit deeper into this, which is with GSK on a type of molecule, covalent drugs, to predict reactivity. And so this use case might not be so relevant for maritime industry, but I guess many of the technologies are the same. So the idea here is that we have this green part, this warhead, which is the reactive part that reacts with the target. And this is really where we need the high accuracy quantum solver, right? Because this is where the chemistry happens. But we also need to model the rest of the molecule in concert, because there's some interaction and some dipole, for example, and some interaction between them. And so we need to have some sort of embedding methods in which we include both a quantum solver as well as a classical solver to together address model this system and be strategic about what kind of simulation we use where. The next question was, and what kind of feature sets can we generate that will be helpful in predicting, in training these AI on? And so in this case, what we did is just measuring the electron excitation energies over time as just a data set that would be informative for reactivity prediction. And so I think this is quite an interesting approach because it makes you very flexible, right? You can just, as long as you get some sort of informative features, doesn't matter what it is, you can train but as long as it's informative for your AI, you can build a data set that is of extremely high quality that you would not get otherwise to train AI on. And so what you see here on the right is then some type of different types of AI that we did. So in this case, it was a clustering algorithm that was able to screen to large data sets to cluster different molecules with certain properties that was trained on this data set. And so that would work very quickly because it was trained on this high quality data. Now, I think one thing that I wanted to address as well is that once you start diving into these use cases, there's all these insights that you get about the use case, right? About the chemistry that's going on, about the reaction pathways, about the symmetries, about the specifications of what is happening. And that is all kinds of information that you can use to optimize your algorithms. And so in the follow-up work of this work with GSK, we try to do that. So what we try to do is, can we have all these insights that we have about the systems that we are studying to optimize our algorithm and sort of leave nothing on the table, make sure that we use all the trick to squeeze the most out of the hardware. And so this involved a number of steps from specifying the problem. And so one of the things that we did was that we knew we were only interested in a very short time frame. And so we could truncate a big part of the Hamiltonian that we would be interested in, so we could focus our problem. Then synthesize a circuit and apply for a variety of technologies like Pauli twirling and Clifford decomposition, a number of circuits that would further simplify this execution, and then the translation. So that the key point that I wanted to address here is that if we want to make sure that we get most out of the hardware, we can really use the insights that we get from modeling these systems. And if we don't do that, it might also work, but you just leave information on the table, right? You do not optimize and get the most out of the current hardware. Maybe final example that I wanted to show, because also yesterday there was the Nobel Prize for Chemistry, which was awarded for the meta-organic frameworks. Was a brilliant physicist from, I forgot where, maybe someone else knows. But meta-organic frameworks are these amazing structures that have these metal containing with organic parts, but they most of all have these big cavities. And so these are spaces where you can trap other type of molecules and atoms. And so and these structures are very tunable. So we can tune them in such a way that we can selectively filter and trap certain type of molecules. And that makes them very usable for things like carbon capture, but also maybe oil pollution cleaning and all kinds of processes, and also potentially catalytic processes. So first trap certain molecules and then break them apart in some way. So very interesting structures, and also very, very interesting. They very well deserved that they got the Nobel Prize for this yesterday. But the challenge is that if you want to model these, there is an infinite or close to infinite design space, right? There are so many different variables that you can tune, and that makes them very difficult to manufacture, to design, both experimentally as well as computationally. They're also complex on a computer because if you use, on the one hand, if you use high accuracy solvers, you have these metal parts, which makes the chemistry very complex, and you might not be able to simulate them very accurately. But if you use high accurate solvers near the metallic centers, it doesn't scale to the whole systems because these are thousands of atoms, very big systems. And so what we developed here was a sort of hierarchical approach where we first cluster these type of superstructures into the smaller structures and then smaller structures smaller, so that eventually we use a quantum computation only for the sort of the metallic parts where they're most relevant, through embedding methods, then combine them with quantum chemistry technology, and then even hierarchical solvers. And so this doesn't, we still need more quantum compute capability to run this, but at least you have a sort of a scalable framework in which you can start to integrate quantum computations. One of the tricky things that we found here was that you might want to embed the outcomes of these quantum computers in their entirely in these type of embedding methods. But getting the data out of these quantum computers is often a very tricky thing. And so we have a PhD with King's College where we address these type of things. So with George Booth, his group, we address the challenge of sampling excitation wave functions using sort of a partial a technology called shadow tomography, so a partial sampling method to very efficiently get this data out such that we can get it into these type of chemistry methods. So I think I'm already over time soon. So let me close off with a couple of thoughts. So I think the promise of quantum computing is really fascinating, right? Particularly in chemistry, material science, and also particularly for the maritime industry. There are so many, potential to really design new, to change the way we do material design and really fundamentally make it from sort of an iterative process, which goes very slow and time-consuming, towards something that is much more purposeful and much more simulation-led. And so this will be fascinating. But to make it work, we need much more than just, even if it's an exponential speed up of some ground states, it's never going to be enough or interesting for industry to care. And so really to get there, we need much more thinking of sort of on this integration and application level. So think about really what will we run these computers for? Not so much what can it do, but if we have this workflow, where would they fit in? How will we integrate them? How will we think more about size reduction, decomposition techniques, embedding technologies? How do we standardize the interfaces between these multiscale models? Right? If we have this data flow from the atomic scale to the macro, molecular, and system scale, how do we facilitate that data flow? How do we create different types of resource managers to do that? How do we have realistic end-to-end resource requirements where we take into account realistic noise models, not just today's noise models, but those of the future, because that's where industry is going to be interested about. And so really, and then also the full end-to-end perspective from data preparation and loading, and so that there's many challenges along the way. But I think if we address some of these challenges, the future is very bright for material science. There's this quote that I sometimes use from Matthias Streuer from Microsoft that said that, even if it's, that he said that material science is 80% of, what did he say? 80%, 90%, and 100% of 90% of products, and now 100% of services are indirectly dependent on material design. So if only we can address this challenge, it will have massive consequences. So start learning about the realities of the practical realities of quantum. So this was more towards sort of end users. Try to see how quantum fits in, and then if we can learn, then I think we can really make something awesome from this. Thank you.